Okay, we have finished our discussions on Newton's laws of motion. Okay, and now we're gonna apply Newton's laws in some of the forces we see in everyday life. Okay, we have already seen gravity, right? And gravity is very easy. The direction is always down. The magnitude is always mass times 9.8, right? So that's gravity. But there are other forces we see in everyday life, right? For example, friction. So friction is what we want to discuss in this lecture. So if you realize that there are actually different types of friction forces, right? Say if you have a very heavy box, right? You want to push it on the floor, okay? And then if it's very heavy, so you push it, it's not going to move, right? So in this case, you're pushing it. How come it's not moving? Well, you would say, well, because there are friction from the floor on it, stopping it from moving, right? So that's a friction force. And in this case, because the object is not moving, okay, we call it static friction. Okay, so that's a friction force that keeps from a surface, that keeps the object from moving. Okay, and we do have experience with that. Okay, and then so one interesting thing about a static friction is that it's not going to be a constant. Okay, so if you think about it, the box is not moving. Okay, then you can draw for a diagram of the box. With all the forces on it, right? So if I draw it, this is what I can get. The gravity of the box, the normal force from the floor. Now there's a pushing force from the person on it, right? And then there must be a friction force, static friction. But use the subscript S, okay, for static friction. If this object doesn't move, right, you're applying a pushing force. So all the forces must cancel out, right? So in y direction, gravity and normal force, they cancel out, okay? So that's obvious to me. Then in x direction, it's very interesting. So the static friction force is also going to cancel the pushing force. And pushing force is a force the person applies on this box. And you can change that, right? Because you can try, right? You do the experiment yourself. You can try to push it like a little bit harder, it's not moving, and then a little bit harder, even harder, it's not moving. So actually the pushing force you apply on this heavy box can change. But if this thing doesn't move, then that means the static friction force is going to be equal to pushing force, right? In this whole process. So the static friction force is also changing. So it's not a constant. Okay, so don't feel weird. A lot of people, they feel weird when we discuss static friction force and it's changing. Think about it, right? Things around us, okay? Pretty much all of them are changing, right? So you shouldn't assume like forces are going to be a constant, right? Actually, most of the forces we see in everyday life, they are changing, right? They're not constant, right? The only constant force you would say is just going to be gravity. Gravity is m times g always, right? So that's a constant. But other than gravity, all the forces we see in everyday life, they're changing actually all the time. So you shouldn't actually, so actually changing is normal, okay? Changing is very normal. And then constant is very, very rare, okay? You should think that way. So it's not a surprise that the friction force, the static friction force is changing, because look around you, right? Almost everything is changing, okay? So in this case, the static friction force, so whenever the pushing force changes, the static force is going to change, okay? And then they're always going to be equal. But you know that even if the box is very heavy, okay? So if you ask some friends to help you, right? And then all of you are pushing, eventually you may get this thing to move. So the friction force is going to stop you, right? If you increase the force, the static friction is also going to increase. But there's some threshold. There's some maximum static friction force from the floor on the box. If you want to get this box to move, all you need to do is just overcome the maximum force, right? Once you have overcome the maximum force, then that's then it's not gonna hold this object anymore. So it's gonna start to move. The object is gonna start to move. So we have found an empirical equation to calculate the maximum static friction force, okay, which is this equation. So the maximum static friction force, okay, from the surface on a certain object, that's almost a constant, okay, but this is still empirical law, okay, so it's not as accurate as Newton's laws, okay, but still it's accurate to a very good degree in macroscopic physical systems. So we can use this empirical law to make predictions, very precise predictions. Okay, but remember, this equation only helps you to calculate the maximum static friction force, right? The actual static friction force, okay, when you're pushing it and it's not moving, you cannot figure it out. You have to draw a Hilbert diagram and use Newton's laws to find it, right? So it's always going to be equal to the external force applied on it, trying to move it, okay? So this Fn, that's the normal force. Okay, the mu_s is the coefficient, so obviously it doesn't have any units, right? You see that this is a force, so this guy can't carry any unit, otherwise the units are not going to be equal. So this mu_s is a dimensionless coefficient. It's called coefficient of static friction, okay? That's just a name we call it. So the symbol we use for it is the mu, the Greek letter mu, okay, with the subscript s, okay? So that's how we find the maximum possible static friction force from the surface on an object on this surface, okay? That only helps you find the maximum. So that's what happens. Take a look at the this image on the second slide. That's what happens when you push something on the surface, right? You push it with the force, it's not going to move, so the surface is going to provide a static friction force with the exact same value as the pushing force, right? And then you push it a little bit harder, the static friction force from the surface is also going to get a little bit larger, again, to balance the pushing force, okay? And then if you want to push this thing move, you're going to overcome the static friction force. Once you have overcome the static friction force, it's going to start to move, okay? The maximum static friction force. And then the static friction force is going to be replaced by kinetic friction force, okay? So we're going to discuss kinetic friction force in a little bit. So we use the symbol Fk for kinetic friction force. We usually use F sub s as a symbol for static friction force. So the cause of static friction force is because the roughness of the surfaces, okay, in contact. So some surfaces, they may look very smooth to you in macroscopic scale, but in microscopic scale, okay, there are still a lot of bumps on these, two surfaces. So when they are in contact, and there's some you want to move one object on the surface, so these bumps, they're gonna, push against each other. So that's why the surface is gonna stop this object from moving, okay? And then because the forces between these bumps are action and reaction, right? Think about it. The surface at the bottom has some bumps, right? And the object, the bottom of the object also has some bumps, right? These bumps, they are pushing against each other. So the forces between them are going to be action and reaction. So the action and reaction, they are always equal in an object. So that is why the static friction force from the surface, okay, is actually the net force from all these bumps against each other, right? So that is why when these two surfaces, okay, these bumps, they push against each other, the forces between them are going to be equal in object. So when these bumps, they are pushing against each other like a little bit harder, okay, like the static friction force is also going to get larger. So So that's why static friction force is not going to be a constant. It's always going to be equal to the pushing force from the outside. Okay. So and then in the next slide, I'm showing you a simulation. Okay, a simulation on the static friction force and the kinetic friction force. So you can see that when a force is applied to an object on a surface, and then you increase the external force, okay, trying to move this object, the static friction force actually is going to increase and increase, right, until it reaches the maximum, okay. So that's because the external force you apply on this object is also increasing, right? You're increasing the external force. You want to move this object. The static friction force is also going to go up, okay? Go up against the pushing force until the static friction force reaches the maximum, so it cannot hold this object anymore, right? It cannot balance the external force anymore. The external force is going to win, but very interesting, when the external force overcomes the static friction force, then the static friction force becomes kinetic friction force, and the value is actually going to drop. Okay, you can see that that's a sudden drop when after the static friction force has reached the maximum. Okay, so the kinetic friction force. So after that, first of all, it's going to be smaller than the maximum static friction force, right? You shouldn't say that it's smaller than static friction force, because static friction force actually has a range, right? So the actual static friction force actually can vary between 0 to the maximum value. Okay? So the kinetic friction force is going to be almost a constant, right? You take a look at the kinetic friction force after the sudden drop, okay? So the kinetic friction is actually almost a constant, but the friction force can change from 0 to a maximum value, okay? All right, so as I said, this is an empirical law, okay? So this is not like as fundamental as Newton's laws, okay? But still we can use this empirical law, this approximate model to make a very accurate predictions in macroscopic physical systems in everyday scale. So that's why we still use this theory, because the static friction is still very complicated. It's actually a very complicated topic. There are still people doing research on friction force. Okay. But this is a very useful empirical law. We can use that and make a very good predictions. And this mu s, as I said, this mu s is called the coefficient of static friction. So there's no fundamental theory to predict the coefficient of static friction between two surfaces. The only way to find the mu s, this coefficient of static friction, is to do experiments. Okay, so if you want to, you have an object on the surface, or on the surface. You want to find the mu s between them. The only way you can find it is just do experiments repeatedly. Okay, there's no way you can use another theory to derive the mu s between these two surfaces. You have to do experiments. So if you look up table of coefficient static friction, you can see, for example, I have included a table on this slide. You can see the mu s between different surfaces. Okay, they have been determined by experiments. Okay, so how do you determine mu s between two surfaces, between an object and a surface in an experiment? So I can tell you a very simple experiment that can be used to determine the coefficient of static friction between two surfaces. Of course, this is not very accurate, but that's something we can do in a classroom, okay, in an intro level physics class to determine the mu s. Okay, so let's take a look at the experiment on slide 6. Okay, so we also want to use this experiment to learn how to work on an incline. Okay, so the experiment is this. Say if I have a surface, right, and then I place horizontal. Okay, I have a surface horizontal, and then I'm going to place an object on it. So what I can do is this, right? I can fix one end of this surface, like in this image, right? And then I can lift the other end. Okay? So if you have a surface, right? You fix one end, you lift the other end. You place the object on this end, on this surface. You know that in your experience, if you live here, right? At some point, the gravity is going to start to pull this object down, right? But it may happen at a certain angle, right? When the angle is very small, the object can still stay on the surface because of the static friction, right? So we're going to use that to determine the mu s. Now think about it, right? When you start raising this one end of the surface, right? So gravity is going to try to pull it down, but static friction is going to keep it on the surface. You keep raising this. Surface. So the static friction, it's going to increase and increase, right? But it still wants to keep this object on the surface. And once you have reached an angle, right? Then this object is going to start to fall. That means that it has already reached the maximum static friction. And gravity is going to overcome the maximum static friction, so it cannot keep this object on this surface anymore. So that's why at a certain angle, this object is going to start to slide down this incline. So we can use that critical angle to find the mu s between the object and the surface. So that's what we want to do here. So how do we do that? Now let's first draw a Fibber diagram. So if I lift the surface at an angle, right, and then the object still stays on this surface, okay, let's draw a Fibber diagram of this object. So how many forces on this object? Gravity is on it, right? Gravity is definitely on it. Normal force is on it, right? And normal force is perpendicular to the surface, remember, that's the direction of normal force. So it's not always straight up, okay? Some people, they may make this mistake, okay? We have seen a lot of problems that I draw gravity down, normal force up, so it's always like that. No, normal force is always perpendicular to the surface, right? If you have a horizontal surface, of course the normal force is straight up, right? But in this case, it's not going to be straight up, it's perpendicular to the surface. You should draw the normal force this way. Right? So that's how you draw the normal force. Now there's also static friction, right? To keep this object on this surface, right? Otherwise you see that these two forces, they're not going to balance out each other, right? If this object stays on the surface, okay, on the incline, all the forces must cancel out, exactly, right? That's Newton's laws. So there must be a static friction force. And the static friction force is always parallel to the surface. So again, it's not always horizontal, right? The simplest case, if you have something on a horizontal surface, so normal force is straight up, static friction force is going to be parallel, it's going to be horizontal, right? But the friction force is always parallel to the surface, right? So if the surface has an angle with the horizontal, so you're going to draw the static friction force this way. So that's the direction of the surface, right? So these two guys, the normal force and static friction force, they always pair up, right? They always come from the same surface, right? If something is on the surface is supporting it, so it has a normal force, and the surface, if it's the surface is not frictionless, there may be a friction force from the surface on this object if the object tries to move or it's already moving. So now, how do we work with these three forces, right? They're in different directions. Well, you're going to break them into x and y. That's what we usually do when we see vectors, right? You always break them into components and then you work with the components. You can never work with these vectors directly. So when something is on incline, okay, instead of using the normal x and normal y, okay, we use another set of coordinate system parallel as the x-axis and then perpendicular as the y-axis. Okay, why do we do that? Okay, the reason is this. If you still use normal x and normal y, right? Because as physicists, we always want to do things, try to find an easy way to do the calculations, right? Even though the theory is the same, but sometimes we want to find an easy way to do the algebra. If you still use a normal x and normal y, so you can count how many forces you want to break. You need to break. Gravity you don't need to break, right? Because gravity is already in the y direction. So you would have these 3 forces if I put them in this x and y. Gravity is this way, normal force that way, static friction force this way. So how many forces do you need to break? You're going to break normal force and friction force, right? If you want to break them into components and work with components. So 2 forces you need to break. But if you use the parallel and perpendicular, okay, to the incline as the x and y, so let's see how many forces you're going to break. So now I'm not going to use that as my coordinate system, right? I'm going to use the a new set of system, coordinate system. Okay, I'm going to use this as my x and y. Okay, so okay, some people I think they like to draw the x in that direction. It doesn't matter, right? It doesn't matter which direction you call positive. If you use this coordinate system, okay, how many forces do you need to break? Only gravity actually, because the static friction force is going to be on my x-axis, normal force is going to be on my y-axis, right? So the only force I need to break is going to be gravity. So you see that if you use this coordinate system, okay, your algebra, your calculations are going to be easier. Okay, that's the only reason we use this coordinate system on incline. Okay, instead of the normal x and normal y, horizontal and vertical, the only reason is that the calculation is going to be a little bit easier. Okay, you can do everything fine using this coordinate system. Okay, no problem at all. Okay, this is just going to be a little bit easier, make our algebra a little bit easier. That's the only reason. Okay, so when I see an incline, I will just use that instead of the horizontal and vertical. Now if I use that in this case, so if I have this object stay on this incline, so I would have this, right? I would have the net force in x direction. If I apply Newton's second law, it's going to be the sum of all the forces in x direction. That's going to be mass times acceleration in x direction. And what is the acceleration in x direction? Remember, now I call this x direction. But it doesn't matter which direction you call x direction. This guy, this object stays on the surface, not moving at all. The acceleration is going to be 0, right? So it doesn't have any acceleration. It doesn't even have velocity, okay? So that's going to be the first equation I set up in x direction. And I do the same thing in y direction, right? Net force in y direction is going to be equal to the sum of all the forces in y direction, and that must be equal to mass times acceleration in y direction. And what is acceleration in y direction? 0. Still 0 in this case, right? If the object stays on this surface. Now I can do this. Find the components in x and find the y components and x components, put them in these 2 equations and see how we can find the mu s. Remember, don't forget what we're doing. We want to use this as an experiment to find the mu s, okay? So I want to show you that how to find this mu s in a real experiment. That's what we're doing, okay? So how many components in x direction? Fs is in x direction, right? So this equation is going to become Fs, and then the gravity is going to have a x component, right? So, because now you see that you're going to break gravity into x and y, okay? Normally you don't, because if you use the normal x and normal y, you don't need to break it. It's already on your y-axis. But now I'm using this x and y. So I will need to break this mg into x and y, so that's how you break it, right? So you need to rotate your head a little bit. Or if this is a piece of paper, you rotate the paper a little bit, right? If you like. Okay, but anyway, you're going to break it into x direction, right? So this is going to be the x component. And then you're going to break it into y component. Right? So this is going to be mg y component. This is going to be mg x component. Right? And then, of course, mg x component is going to be negative. So you would do this. That's going to be the all the components, all the forces in x direction, and then the sum is going to be 0, right? And which is intuitive, right? Because I know that if you tell me that everything is going to cancel out in x direction, of course this force is going to be equal to that force, which is what you're going to get, right? Fs, static friction force, equals the x component of gravity. Now you do the same thing in y direction. In y direction, I have a normal force in positive y direction, so I'll write it down. Right? So that comes from the second equation. Still Newton's a second law in y direction. Now the y component of gravity, again, this is down, right? If I call that up, this is down. So let's give it a negative sign. Mgy, that's going to be 0. So these are going to be the two equations you get. But don't forget, we want to use this as the experiment to determine mu s, right? I still don't see mu s here, okay? Well, that's when we raise this, incline, okay, until it's going to reach. So first of all, you're going to start from horizontal. So of course, this block is going to stay on this surface, right? You start raising it, right? So at some point, the Fs is going to become the maximum, okay? And at that point, that's going to be critical angle, right? If you keep raising it a little bit, it's going to start to fall, okay? Slide down this incline. So that's when the static friction force has reached the maximum, okay? So if you have found the critical angle theta, say if this object starts to fall, starts to slide down right at the angle theta. Okay, the theta angle can be 40 or 50, right? You do the experiment, you find that. But that's going to be the critical angle. At that point, the static friction force is going to become the maximum, right? So we can see that y is going to become maximum at that angle, right? So first of all, let's find the x and y components of gravity. So then you see that if I want to find x and y components of gravity, I can use this right triangle. So again, you use this right triangle, okay? You use trig. Gravity is the hypotenuse. So if I say I know the mass of this object, so this is going to be a number I know, right? So now we're working again with all the symbols. We want to find a general conclusion how to use this experiment to find mu s. So we want to find a general expression for mu s. That's what we're doing. So I'm going to use mg, but then I need an angle theta, right? I need an angle, okay, to help me find the y and x components. I can do sine and cosine, right? There's a theta angle here, okay? So you sort of need to move this theta angle, transport this theta angle to this right triangle so that you can use that, okay? So how do I transport that angle to this right triangle? So, okay, so you're gonna use some of the right triangles here, okay? You're gonna use some of the right triangles here. So, I'm not going to do it here because I don't want to make it too messy. So I'm going to, no, I guess I can do it here. So if this is a theta angle, okay, and then you can see that this is theta angle, right? If this is a theta angle, right, because these two lines, there's the same line. This is parallel, right? If this is theta angle, this is theta angle, right? If this is theta angle, take a look at this right triangle here, because this is a gravity line, so this is totally vertical, right? So if I take a look at this right triangle, take a look at this one. This is a right triangle, right? Because this is vertical line, this is horizontal line. If this angle is theta, what is this angle? Oh, that's going to be 90 minus theta, right? So this angle must be 90 minus theta. And if this angle is 90 minus theta, this angle must be theta. Why? Because this is a right triangle. This big angle, okay, made by these two axes must be 90, because this is 90. If you tell me this is 90 minus theta, this angle must be theta, right? So you see that this angle between the mg and the y component of this mg is going to be theta angle, okay? If the problem tells you the incline angle, okay, if the incline angle, I find the incline angle. So how do you use this theta angle to find mgx and mgy, right? So let's take a look at mgy. That's going to be hypotenuse, this is hypotenuse, this is theta, this is adjacent. This y component is adjacent. Adjacent, you should use cosine, okay? So this is going to be equal to mg cosine theta. All right? Then what about x component? X component is this side, which is also this side, right? If you look at this side, that's going to be in this right triangle. That's going to be hypotenuse, and then this is opposite. You're looking for the opposite. You're going to do hypotenuse times sine this angle theta. Okay, so now you see that in this case, y component is mg cosine theta. X component is mg sine theta. A lot of people, they would ask, why? We have been using cosine theta for x and sine theta for y. Again, that's what I said earlier. You don't need to remember the shortcuts. The problem can give you a different angle, right? In this case, the problem gives me this angle. Once I have transported to this right triangle, I realize it's this angle, theta. If this angle is called theta, not that angle, right? We call this angle theta. This is how I'm going to get the x and y components, okay? Y is going to be cosine, x is going to be sine. So there's no rule, there's no law saying that every time you get a theta angle in the problem, you want to find x components, it's got to be cosine. You see a theta angle from the problem, you want to find a y component. Doesn't matter what this problem is, you do sine theta. No, we never learn a law like that. So don't remember these shortcuts. Don't remember these special conclusions, right? As I said, draw it out. You draw the diagram, you draw these two components, find the right triangle. Go from there. Use trick. You can always find the right function, cosine or sine, right? Because the problem may give you a different angle. The problem may give you an angle which is not in the right triangle you want to use. So now you're going to use some relation between these angles to find an angle in the right triangle you want to use, right? Okay? So in this case, we found that mgx is going to be mg sine theta equals 0. And then the normal force is going to be negative minus mg cosine theta equals 0. So that's how I set it up, right? Now and then you see that, oh, so this equation actually just tells us that static friction force is going to be equal to mg sine theta. And normal force is going to be equal to mg cosine theta. Right? Now you can see that why this static friction force is going to increase as you raise this incline, right? So if you do math, everything is clear. Everything is very easy to explain. If you raise this incline, the theta angle is going to get larger and larger. And then if the object stays on this incline, you always get this equation, right? This is always true, these two equations, because they're Newton's laws, okay? mg is not going to change because the same block. But if the theta angle gets larger and larger, the Fs, the static friction force, must get larger and larger and larger in order to keep this object on the incline, not moving, right? And we know that static friction force has a range, right? It cannot go bigger forever, right? It has a limit. The limit is the maximum static friction force we call. And the maximum static friction force is related to the normal force. We have a good equation for that, even though it's only an approximate model, but this is good enough. We can use that to make very good predictions in everyday life, okay? So if you keep raising this incline, okay, very slowly, right? So it's gonna be staying there, okay, stay there, stay there. At some point, you can see that once you have found the critical angle, then this block is gonna start to slide down. That's when the static friction force has reached the maximum, right? So if you can find the critical angle theta, right, say like 40 degrees, I realize if I raise it very close to 40 degrees, then it's gonna start to fall. Before 40 degrees stays there. Once I reach 40 degrees, it starts to fall. That's gonna be the critical angle, right? At that critical angle, the static friction force is gonna become the maximum, right? At this critical theta. Okay, so if you still use these two equations at the critical angle, what do you get? You will get this. At this critical angle, I would have F maximum static friction force equals mg sine theta, the very critical angle. Normal force equals mg cosine theta, right? Okay, how do I use this? Don't forget what we're doing. We want to use this experiment to find the mu-s. How do you use this? How do you go from here to find the mu-s? Now I can incorporate mu-s in that equation because the maximum static friction force equals this. So now I can plug it in, right? Because the actual static friction force is going to change from 0 to this. But once I have found the critical angle, that's when the maximum static friction force has been reached. So, okay, so I can replace that with mu-s, normal force, equals, so this is all at the critical angle theta. All symbols, because I want to draw a general conclusion. Now you see that you can use these two equations to find an expression for mu-s. That's going to be the expression we use in this experiment to find the mu-s between these two surfaces, okay? So how do I use these two equations to find the mu-s, okay? You see that you already have the expression for Fn. If you plug it in, rearrange this equation, you will get a very nice expression for mu-s. So that's what I want you to answer on slide 7. That's the question on slide 7, okay? So you can finish this algebra, find this mu-s, okay? All right, so let's see. What is your answer, okay? If you plug the mu-Fn in that first equation, you get mu-s, right? Because mg cosine theta equals mg sine theta. And you divide both sides by this guy, what do you get? Mg is going to cancel, right? Mg sine theta over mg cosine theta. Mg and mg cancel. Sine theta over cosine theta, what is that? Tangent theta. So that's going to be the answer, right? So you see that if you do this experiment, okay, you don't actually need to know a lot of details, okay? All you need to do is just place this object on the incline. Fix the one end of the incline and raise the other end very, very slowly, right? You can't do it really quick because you want to find a critical angle where the object just starts to slide down. You can do it very, very slowly, raise it very, very slowly, okay, still on it, still stays there until you found the angle, where this object starts to slide down, you're going to record that angle. And then you do all this algebra, you find that, oh, I need just the theta angle. I don't need any detail about the surface, the object, right? I just do tangent theta, I will get mu s. Okay, so that's how we use a real experiment to determine the mu s, the coefficient of static friction between two surfaces. Okay, of course this is very primitive, right? This is not going to give you a very accurate value, but this is a idea I want to show you how we can find. The idea is that I want to show you how we can find this mu s in a real experiment. As I said, this mu s cannot be predicted from any fundamental theory, so that I give you two surfaces, you use the fundamental theory, you can just find it. Okay, you have to do an experiment. You have to come up with an experiment to find the mu s between these two surfaces, and this is one of the simple experiment you can do. Okay, so again, a lot of people at this point, they would ask me, do I need to remember this? This looks like a very nice conclusion. No, you don't. Okay, I've said many times, physics is not about memorizing these conclusions and shortcuts. How did we get there? We used the Newton's second law. Still the same theory we learned for any force, any motion, right? We just used the same theory, okay? Applied it on this very special situation, and then we picked a very different coordinate system, applied the Newton's second law, break vectors into x and y directions. Pretty much everything we learned before, all the skills, all the theories we have learned earlier, we just applied them here in a real life example, and then we finish all the algebra, we get this. Okay? You don't need to remember that. Maybe it's easy for you to remember that, but you shouldn't expect that you will get a question. I'm just going to ask you a question. If you do this experiment, you raise this incline, you add until you see that this object starts to slide down at 30 degrees, what is the coefficient of static friction? Oh, I remember that, that's tangent theta, or tangent 30 degrees. No, you don't expect a question like that on a test, right? That's not physics at all. I'm not going to test your memorization, okay? I'm not going to test your memorization. You don't need to remember this, okay? If I give you a question like this, I would want you to start with from the very beginning. Okay, do the algebra, do all the work, and show me you understand the theory we're learning this class, right? You can do everything from the fundamental theory we learn in this class. You don't just memorize this equation and then, hey, I just plug all the numbers and get the answer. No, that's not physics. That's not what we're learning in a physics class, okay? All right, so that's an experiment I want to show you. Now let's take a look at another question. So I want to use this question again to practice this static friction force, especially this maximum static friction force equation we just learned. Okay. Now, no, I guess I'm gonna stop here, and then we're gonna do this next time. Okay. Okay, I'm gonna stop here for this video, and then we're gonna see an example with real numbers next time.